Time traveler, imagine for a moment an unrecognizable Earth, a billion years in the past. A world without dinosaurs, without towering trees, or the vibrant burst of colors from flowers. Instead, we find ourselves in an era where the atmosphere was just beginning to breathe oxygen, painting the skies in unusual reds and oranges. Vast oceans, often tinted by microbial activity, covered the planet, while nascent continents, like drifting puzzle pieces, formed a gigantic supercontinent, Rodinia. There were no trees here, no animals, no flowers, just primitive bacterial mats carpeting the seafloor, transforming the planet's chemistry. On the surface, active volcanoes spewed lava and gases into a dense, suffocating atmosphere, shaping a landscape as hostile as it was fascinating. Primitive Earth, a billion years ago. A billion years ago, Earth was radically different from what we know today. We're in the Neoproterozoic, the last era of the Proterozoic eon, stretching from approximately 1 billion to about 538 million years ago. Complex life was barely a whisper here. Even though cyanobacteria, the true architects of photosynthesis, had been releasing oxygen for eons, the atmosphere's composition was still very different from today's. The air was thick with volcanic particles, and sunsets, if not hidden by dense ash clouds, offered a spectacle of intense reds. The landscape, devoid of any vegetation, was an arid, rocky expanse, likely dominated by mountain ranges formed from intense tectonic collisions. The constant fury of volcanoes spewed lava and gases, sculpting a terrain as hostile as it was fascinating. Plate tectonics were in full swing, constantly reshaping the planet's surface. Oceanic crust was created and destroyed in a continuous cycle that repeatedly changed the distribution of land and sea. Rodinia, that colossal supercontinent that fused fragments of what we now know as North America, Siberia, or Australia, dominated the geography. The geological structures our cities stand on today were, hundreds of millions of years ago, part of this single landmass. The dance of oxygen and the ice ages. As Rodinia formed, the atmosphere continued its slow transformation. Oxygen levels kept rising, though not steadily. These variations would play an important role in the future evolution of life, creating the necessary conditions for the emergence of multicellular organisms. However, the Neoproterozoic would give us one of the most extreme climatic episodes, the Snowball Earth glaciations. The planet turned into a gigantic ice sphere, with layers extending from the poles to the equator, and oceans covered by an icy blanket that in some regions could be several miles thick. In this incredibly hostile environment, life, astonishingly, persisted in tiny refuges, like hydrothermal vents on the ocean floor, or in areas where light could penetrate the ice, allowing microbial communities to survive in small, protected ecosystems. The exact causes of these glaciations are still debated, but the most accepted theories point to a combination of geographical and atmospheric elements. On one hand, the arrangement of Rodinia's continents near the equator might have significantly altered ocean and atmospheric circulation patterns. On the other hand, a reduction in atmospheric carbon dioxide, possibly associated with increased weathering of exposed silicate rocks after continental fragmentation, would have decreased the greenhouse effect, favoring global cooling. Rodinia's disintegration, a gradual process that would last millions of years, drastically altered ocean currents and global climate. The same internal forces that contributed to its formation began to pull it apart from its base. Cracks and ocean basins opened up, significantly altering the flow of ocean currents. Traces of that breakup can still be found in many regions of the world. Curiously, volcanic activity, which had shaped the surface, also released carbon dioxide, a greenhouse gas that, accumulating under the ice sheets, since it couldn't be absorbed by the oceans or fixed by the land surface, would eventually reverse the glaciations, melting the ice in a geologically short period, possibly just a few thousand years. Life's first complex experiments, the Ediacaran fauna. Emerging from the icy grip of the glaciations, we enter the Ediacaran period, a crucial time of recovery and stabilization. Sea levels rose, flooding vast areas of newly formed continents, the result of Rodinia's fragmentation, and creating warm, shallow seas rich in nutrients released by the weathering of rocks, exposed during the glaciation and deglaciation cycles. Earth, once a microscopic laboratory, transformed into a planetary incubator, where conditions began to stabilize, allowing for biological experiments on an unprecedented scale. Oxygen concentration in the oceans and atmosphere continued its ascent, a vital factor for the development of organisms with more complex metabolisms, and consequently larger sizes. It's here that we find the first complex macrofossils that were neither bacteria nor algae, the enigmatic Ediacaran fauna. Organisms with quilt-like or frond-like shapes, like the famous Dickinsonia, a creature that could reach over a meter in length and resembled a segmented oval mat. Others, like Sprigina, showed possible bilateral symmetry, a characteristic that would become fundamental in most later animals. Many lacked mouths, complex guts, or circulatory systems in the modern sense, suggesting they might have fed by absorbing nutrients directly from the water or from the microbial mats covering the seafloor. They were predominantly sessile or had very limited movement, inhabiting a world without active predators. These beings, which emerged around 575 million years ago, represented nature's first major experiment with multicellular life, the prototypes of animal complexity. Life was learning to build, to form structures. Although many of these designs didn't last, their existence is a fascinating testament to how evolution explores different paths. The disappearance of the Ediacaran fauna towards the end of the period is a topic of scientific debate, but the arrival of new Cambrian organisms, with their mouths and grasping appendages, and their ability to disturb sediment, may have been a key factor. The Ediacaran was the quiet prelude to what was to come, an evolutionary laboratory where nature tried out different forms and strategies for multicellular life. The Cambrian Explosion, an unprecedented dawn. And then, we reached the Cambrian period, spanning from approximately 538 million to 485 million years ago. This wasn't just another chapter in geological history, but a radical turning point, an unprecedented burst of biological diversity known as the Cambrian Explosion. Suddenly, the fossil record reveals the appearance of most of the major animal phyla we know today. This doesn't mean they appeared out of nowhere. Evolution is a gradual process that had been brewing at a molecular level for millions of years, as we saw in the Ediacaran. Rather, it was a moment when organisms first developed skeletons, shells, and other hard mineralized parts that fossilized more easily. This marked a fundamental shift. For the first time, animals could protect themselves from predators, anchored to the substrate, or move more efficiently. The Cambrian seas were now vibrant, greenish or brownish, and the seafloor, once covered by extensive gelatinous microbial mats, was being colonized by an astonishing variety of new life forms. Earth was in a mode of biological acceleration, producing a myriad of body plans. The evolution of complex eyes, like those found in trilobites, allowed animals to perceive their environment in a completely new way. Suddenly, seeing and being seen became a matter of life or death. Trilobites, with their segmented bodies and remarkable compound eyes, some with thousands of individual lenses, became iconic fossils of this period, with over 20,000 described species, populating seafloors at all latitudes. But they weren't alone. Alongside them emerged the first mollusks, like primitive cephalopods and gastropods, brachiopods, with their bivalve shells, echinoderms, like primitive sea cucumbers and starfish. And crucially, the first chordates, the precursors to the vertebrates from which we descend. Tiny organisms like Pikaia, an eel-like animal with a primitive notochord, a flexible rod that's the precursor to the spinal column, represent one of the first steps toward our own evolutionary lineage. The emergence of active predators, like the formidable anomalocaridids, which could reach up to a meter in length with grasping appendages for catching prey and compound eyes, revolutionized food webs. Their very existence changed the game. Before, life primarily fed by filtration or passive grazing on microbial mats. Now, a complex interaction of hunting and evasion existed, further driving the diversification of body forms and survival strategies. Life didn't just diversify into new forms, but also into new behaviors, like bioturbation, deep burrowing into sediment, which destabilized the ancient microbial mats. Geologically, the Cambrian was a relatively calm period, without massive global glaciation events that would refreeze the planet. Warm, shallow seas facilitated the precipitation of calcium carbonate, an essential element for building the new skeletons and shells. Erosion from emerging land masses supplied nutrients to the oceans, fueling this explosion of life. The Cambrian explosion wasn't an instant event, but a period of tens of millions of years where the rate of evolutionary innovation skyrocketed, leaving a fossil legacy that still fascinates us today and reveals the origins of animal complexity. The planet, once home to simple life forms, was transforming into a vast, complex marine ecosystem, a prelude to the wonders yet to come. Would you like us to keep exploring the eras that followed, like the Ordovician and the diversification of the oceans, or the Silurian with life's first steps onto land?